Uh, Hi everyone. I'm Hardepinder Singh, PhD student at NIT Uttarakhand, India. I'll be presenting my latest work titled Influence of Interfacial Spilled Glass Like Disorder and Frustration on Exchange Bias Characteristics in Interdiffused MNF Bilayers. This work has been recently published in Applied Physics Letters. So I'll be starting with a brief review of exchange bias phenomena. And actually, exchange bias is one of the oldest phenomena and the most studied phenomena in magnetism. It is rich of physics and has technological applications. It can be defined as a coupling between the ferromagnetic and antiferromagnetic spins at the interface. As you can see in the figure, without antiferromagnet, there is no shift in the hysteresis loop, whereas as soon as antiferromagnet is brought in proximity to ferromagnet, there is a shift in the hysteresis loop, which is basically the exchange bias field. This can be understood in a better way like this. Suppose if the system is brought under a temperature below the Curie temperature of ferromagnet, but above the neat temperature of ferromagnet, antiferromagnetic spins remains random, whereas ferromagnetic spins gets aligned. But as the field cool is done below the Néel temperature, the antiferromagnetic spins gets aligned ferromagnetically, and to maintain the AF order, the next AFM planes arrange antiferromagnetically so that the net charge is zero. Now, when the field is rotated or turned, ferromagnetic spins try to turn, but antiferromagnetic spins, due to this interaction, exchange bias interaction, tries to keep them in original position. As a result, excess or extra field is required, which results in this shift of the hysteresis loop. So this is the whole process behind the exchange bias. Now, exchange bias forms basically the integral part of spin walls and MTJs, which are the building blocks of current spintronic devices such as hard disk drives and magnetic random access memory. So I'll be discussing two of the features of EV which are relevant to the present work. So firstly, what is asymmetric magnetization reversal? It is basically different magnetization reversal at the ascending branch and descending branch. It can be seen as like at the ascending branch, you can see there's a coherent magnetization rotation, whereas at the descending branch, it's a domain wall nucleation. So different kinds of magnetization reversal is observed in AV systems. The origin of this is due to higher order FM anisotropies like biaxial anisotropy, local misalignment of easy magnetization axes of ferromagnet and antiferromagnet layers. Second feature is the training effect. It is the decrease in EV after consecutive hysteresis measurement. As you can see, there's a reduction in the exchange bias after number of hysteresis measurements. It is due to the metastable or non-equilibrium state of the AFM-FM interface and has been linked to rearrangement of the interfacial FM spin structure. So normally, most of the FM which have been used in spin walls have been like NIMN, FEMN, PTMN, and IRMN. But NIFN and FEMN has poor corrosion resistance and low exchange bias. So the most commonly used antiferromagnet presently is IRMN, which is, as you can see in this figure, in the last few years, its price has increased quite highly. That's why it is very rare, and it causes greenhouse emissions and also leads to depletion of water. So we need to search for an alternate antiferromagnet, and MNN can be a good prospect for this. Now, MNN is basically a phase of MNN alloy, and it has shown to have a very high in-plane EB and perpendicular EB. It also shows a large blocking temperature. Blocking temperature is a temperature at which EB vanishes, so it can be good for automotive applications. And thermal stability can be also controlled using nitrogen content of MNN. And since MNN is quite abundant with respect to iridium, and nitrogen is the most abundant gas in the atmosphere, so the price, there's no issue in terms of price. It has tetragonal phase variant of NaCl structure, and magnetically it is of antiferromagnet of A type, that is spins are the coupling between intraplane is ferromagnetic, whereas interplane coupling is antiferromagnetic. So what are the issues basically in the despite showing a lot of promise, there are certain issues which needs to be addressed before MN's incorporation in spintronic devices. Basically, most of the studies have been done on the tantalum buffer layer, which gives 0-0 orientation to exhibit large exchange bias. However, these have shown to be thermally unstable. As you can see here, at above 375 degree, EV suddenly decreases, and also below thickness 20 nanometer, exchange bias decreases. Since to be incorporated in EV devices, the thickness should be around 10 nanometers. So one needs to look for other buffer layers and other substrates. Further, the origin of EV is also not understood properly in this. Hence, and there's no temperature dependent study and training effect studies also. So our objective in this work was to study the growth of MN FE thin films on tungsten buffer layer. This is a new buffer layer which we have used. We wanted to study the origin of EB phenomena by investigating the thermal evolution of EB reversal asymmetry and training effect. So this system was stack structure was deposited on thermally oxidized substrates, which are industrially useful, and pristine sample was termed as S1. Now here you can see tungsten is a buffer layer, antiferromagnet of 40 nanometer, iron was used as ferromagnet, and tantalum was capping layer to prevent the oxidation. So annealed sample was named as S1300. It was annealed at 300 degrees centigrade for 15 minutes in presence of 1.5 kilo resisted magnetic field. It was structurally characterized using X-ray reflectivity and X-ray diffraction, and magnetic characterization was done using MOOC and SQUID. So firstly, we'll see the X-ray diffraction analysis. So as we can see here, for the ash deposit sample, it clearly showed peaks of alpha tungsten and Mn00. It had grown in 0-0 orientation. It showed a latest parameter of 4.30, which is little bit more than the observed latest parameter of 4.28. And as it was annealed, it showed a slight shift in the peak position of Mn002, which indicates a little bit reduction in the latest parameter, which could be due to the nitrogen out diffusion as observed in other literature also. But overall, the stack remained stable at this in temperature. Further, we examined thickness and roughness using X-ray reflectivity, and as you can see in the figure, during 0.05 to 0.8, we can see the sample S1300, which is the annealed sample, the amplitude of the chiastic fringes getting little bit lesser due to the increase in the interface roughness, which is also corroborated by the simulation of X-ray reflectivity. As you can see, there's a 4-fold increase in the roughness. Further, we examined the scattering length density versus the depth profile of this system, and we observed that there was a gradual transition in both the samples. However, the sample S1300 exhibited much more gradual transition, indicating the interdiffusion at the interface. And this is also confirmed by the increase in density of the MNN and decrease in the thickness of the MNN. Further, diffusion was toward the iron, and as you can see, the density of the iron also reduced due to the night radiation, and thickness of the iron also increased. Further, it is important to note here that the interface between Mn and tungsten did not show any, it showed a sharp transition, which indicated there was no diffusion towards tungsten. It is important here to note that because in previous works, tantalum, which was used buffer layer, the diffusion was mostly towards the tantalum. So further, we did MOOC analysis, and as we can see here, that for the ash deposit sample, there was negligible EB, and coercivity was also same of 280 arrested in all three directions, showing isotropic behavior. Whereas for S1300 sample, it showed EB of 118 arrested and reduced with increase in the MOOC angle. And coercivity also reduced, and with MRMS ratio also showed a decrease with increase in angle showing uniaxial behavior. This was further confirmed by basically angular dependent coercivity study, and we observed two minimas suggesting uniaxial anisotropy, which was also fitted by this equation, and we got negligible value of biaxial component comparison to uniaxial component, suggesting that the main component of anisotropy was uniaxial in this sample. Further, we did squid hysteresis loop at basically we studied temperature dependence from 300 to 10 Kelvin, and we can see here that 300 to 100 Kelvin there was a slight decrease in the slight increase in the EB, which may be due to the thermal stability of the AFM grains. However, below 100 Kelvin and especially at 10 Kelvin, we can see around 10-fold increase and 6-fold increase in 10-fold increase in EB and 6-fold increase in coercivity, along with this kinged asymmetric reversal. This was also accompanied by a sharp decrease in the magnetic moment, which suggests a spin glass-like frustration at the interface. Normally, spin glass-like frustration is seen to show an exponential behavior.
Gentle reminder of the time less 1 minute left. Yeah.
Oh, sir, I'll take 2 minutes. I'll finish. Okay. Further, we did fitting of this, and we found that it fitted well with the exponential function, and it showed a spin glass-like frustration at the surface. Then we studied training effect study, and we observed, we did training effect for 10 loops, and we observed a strong training effect, as you can see in this figure, between first and 2 loops, and it basically showed a confirmed temperature dependent transition from uniaxial to biaxial anisotropy, which was further confirmed by, as you can see at 300 Kelvin, there was no training effect for the uniaxial sample. So we fitted this with 2 different models. First was the thermal relaxation model, which applies to the thermal training effect and is normally valid for n greater than 2, and it fitted for n greater than 2, but this model did not fit for n greater than 1, thus confirming there's a thermal training contribution in this, and this suggesting that there are 2 contributions, thermal and thermal. Further, we fitted this data with spin glass model, which is given by this particular equation, where AF and AI are the frozen spin parameters, and AI and PI are interfacial rotatable parameters. This model basically assumes spin glass disorder at the interface due to the 2 types of spins, rotatable and frozen. Now, rotatable, when field is reversed, gets easily rotated and leads to the increase in coercivity, whereas AFM spin does not rotate, and sometimes it may rotate due to high field, leading to training effect. As we can see here, the spin glass model fitted very well with this data, thus confirming the exchange, confirming the frustration and spin glass-like disorder at the MN interface. So we can see here that AF value, that is the frozen parameter, is very high compared to the AI parameter. That means training effect primarily originates from frozen spins. Secondly, relaxation rate of the frozen spin is 12 times slower than the rotatable spins, which is expected since frozen spins have more anisotropy. And lastly, I'll summarize my work. So we were successfully able to grow 001 oriented MN on tungsten buffer layer. When annealed at 300 degrees centigrade, the structure remains stable, revealing a substantial AB of 118 arrested. Further, temperature-dependent studies showed exponential behavior, indicating presence of spin glass-like disorder at MN iron interface. Training effect revealed 2 distinct mechanisms, a thermal and thermal. Further, spin glass model showed an exceptional fit for these points, providing support for spin glass-like characteristic at this interface. Thank you. Finally, thank you for giving me this opportunity to present at this work, and I thank the organizers for putting up such a wonderful event. Now, I'll be happy to take any question.
Well, since time is quite limited, maybe we only allow 1 small question. Does anyone else have a question?
Can you go to the slide 16?
Yeah.
Yeah, so the equation 2 is the last term is the exponential is missing, or it is the...
Oh, I think, yeah, it is basically missing. I'm sorry. I think it is missing here.
Okay, so I was just curious to know, is it there?
Yeah,
Okay.
yeah, yeah.
Okay, thank you for your time.
Oh, thank you.
Okay, I think time is up. Thanks for Hardepinder for the
Thank you.
good, wonderful talk.